Hello friends, welcome back to our channel Mirror Neuron, which means watch and learn. So first of all, I would like to apologize that we took some time to come back with the part 2 of the neural network series because we have been spending actually a lot of time to think about how should we present the information, because there are so many tutorials online, those actually they are very confusing, and we just wanted to make sure that our tutorial is very easy to consume and you get to understand the internal working of the neural network, and that is why it took so much time. Although we did not do anything fancy like animation or anything, but then we tried to put the information as simple and straightforward as possible. So last time, in part 1, we have been discussing that we'll build a simple neural networks for understanding the logic of an AND gate, and this is the simplest example that we can find and implement this. So today we are going to discuss the basic steps and also see how such a simple steps can be implemented in Python. And once we are comfortable with all these programs and codes, then we will gradually move into TensorFlow or Keras kind of library. But this basic information is very important because tomorrow TensorFlow or Keras might close down or shut down, right? But we should be still able to implement this in basic Python. All right, so this was the AND gate, and we had two input features, which is x1 and x2, and y is our output. And we have also seen this diagram where x1 x2 are fed into a mathematical operation, which is the summation, along with a bias term, and this creates x1 dot beta 1, which is the weight for x1, x2 dot beta 2, beta 2 is the weight for x2, and the bias term, which is beta naught in this case. Okay, and going forward we'll represent beta 1 beta 2 with simpler alphabets like b1 b2 instead of writing beta, right? And once this summation is calculated, we are going to feed this summation value into a sigmoid function, which will basically give us the probability between 0 or 1, or in simple English we can say that the input can be anything between negative infinity to plus infinity, and sigmoid will squish it into 0 and or 1 within the range of 0 or 1. Okay, so the first thing that we would like to understand in neural networks is how to first of all assign this input value x1 and x2, right? This was also the statement that we made last time. And once we give the x1 and x2 into a network, what processing does the network going to do? And once we get some processed data, what we're going to do with that information, and so on. Now what we are trying to do here in this case is we are moving from left to right, right? We are giving the input x1 x2, we are doing a summation when we multiply them with the weights, and then we are feeding this summation value into the sigmoid function, and then we are getting an output. In the neural networks arena, we call it as feed-forward network. Okay, because we are moving from left to right, we are not passing anything from right to left or anything from output towards the input. We are not doing anything like that as of now, and that is why we are calling it as feed forward. And in our subsequent lectures we are going to see something called as back propagation. That means we are going from right to left. That means we'll do some changes, we'll see in more details that we are going from output towards the input, and that's why it's called back propagation. So basically neural networks typically will use both feed forward and the back propagation together so that we can build our optimal solution. Okay, so the first thing that we are going to do is, we are going to import the library numpy as np, and we are going to, for the time being, let's skip this sigmoid function. We'll come back here in a while. So the first thing that we are going to do is take the first input record in our case. So in AND gate, the first record says x1 is equal to 0 and x2 is equal to 0, right? And basically we want to predict that our solution will be 0 because in AND gate, x1 times x2 should give us 0 basically. All right, so but how our model is going to learn? So we will be multiplying this x1 with beta 1, x2 with beta 2, and then we are going to add the bias term to that value. Okay, so in addition to that, we would also like to know that where should we get b1 b2 and bias, or beta 1 beta 2 and beta naught. So basically we start with a random value. In technically you can start with anything. You can start with 0.5, 0.5, 0.5 for all the three cases, or you can totally go with numpy random function and you can just pick any random value, doesn't matter. Okay, so basically what we are going to do, so you are seeing a dotted line here, so anything that we are going to write now is on the left side. So the first thing that we are going to do is write a function so that we can do this basic summation. So we'll be doing x1 times beta 1 plus x2 times beta 2 plus the bias term, and we want to get that output, and once we have that output we'll pass it on to the sigmoid function. Okay, so you can see we have just randomly taken some value for beta 1, beta 2 and beta naught. So you can see the summation factor gives us these values in the red color. It is, so the first x1 is 0, so we multiply it with the beta 1, which is some value, plus 0 because x2 is 0, we multiply it with some value for the beta 2 and plus the bias term, and this we repeat for all the 4 inputs. That means we do it for x1 equal to 0 and x2 is equal to 1, and then we do it for x1 is equal to 1, x2 equal to 0, and then we do it for x1 is equal to 1, x2 is equal to 1. So we basically repeat it for all the 4 records that we have. But here we have just been considering the first 2 records so that you can manually show what's going on. So if you see, the summation is 0.01, right? Because 0 times the beta 1, 0 times beta 2 cancels out, and we're left with only the bias value here. So that means it's 0.019, and sigmoid returns something as 0.4952 and so on. But if you see here, our expected output is 0. But what we got instead is something way far from 0. It is 0.4952 and so on. So we can calculate the error. So our expected value was 0, but we got 0.49. Hence the subtraction gives us minus 0.49. So this is the error from the first row. Secondly, when we calculate the same thing for the row 2, where x1 is equal to 0 and x2 is equal to 1, we do the summation again. And this time our summation gives us something minus 0.0999. We pass this value again to the sigmoid. What we get this time, our expected is 0, but we got 0.5249. Again, quite far from our expected value. Hence, the error is the expected value minus the predicted value. So we get again minus 0.52 and so on. So similarly, we can do this for row 3, row 4, and we get the total error. And once we get all the 4 errors from the 4 records, we will basically sum them up and take the average so that we can get a somewhat understanding that where my things are going wrong. Okay, so far so good. Now this activity, instead of doing manually, we can write a simple Python code to do this process. Okay, so the first thing is np.random.seed, and what does this mean is that because we are playing with random numbers and I might be running this piece of code more than once, so I don't want my random values to change every time. So that's why I want to fix my random values at certain point. So that's why I'm using a seed function here. So every time I run this process, the random values are going to be the same. Why we are doing this? Because whenever you are experimenting with a new algorithm, you want to have some static numbers to compare with. Otherwise, if the number itself keeps changing, it becomes very tough to keep a track of it. So the first function is sigmoid. And as I told you, sigmoid can take values from negative infinity to plus infinity, but then it will give you values between 0 and 1. So let's jump a few slides up where I have created a simple sigmoid function. Here is the Python code if you want to just repeat it along with me. So you see I took a value from minus 10 to plus 10, and if you see my sigmoid function returns value between 0 and 1. Up to a certain point it's 0, then it rises up and then goes to 1. Alright, so this is sigmoid, and this is the purpose of the sigmoid function, to act as a filter, right? So that anything we give it as input, it should try to put it between 0 and 1. And technically, if you think from another perspective, our output also lies between 0 and 1. Specifically, it's 0 and 1, but then we want to keep it within 0 and 1. And that is a very important part of our neural network activity, that whenever when we say our neuron is working, that means it is getting activated. If it is a value within a certain threshold, then it's 0, and if it is beyond that threshold value, it should be 1. So similar to our neuron in our brain, and it activates after a certain threshold, and that's what we are trying to represent here. The function is 1 over 1 plus e to the power minus t. a very common popular function, and it just returns that value between 0 and 1. Okay, now we need some random weights for beta 1 and beta 2 and for the bias. So what we can do, we can use the np numpy random.randn, and I'm just creating two values, one for beta 1 and beta 2 and one for the bias, which is b0. Okay, I could have actually done it within weights itself. I could have created a 1/3 matrix, but I wanted to just clarify where exactly we are going to use this bias. So I can display the weights, okay, and you can see for beta 1 it came out to be 0.44122, and for beta 2 it's -0. These are all random values, and as I said, you don't have to use np.random. You can start with any values you want, but then just everybody does it, so I'm doing it using the np.random.randn, and then we have a bias weight which is 2.43 and so on. Also, now we are passing the input data as well, which is from our AND gate, and input can be presented this way: 0 0 0 1 1 0 and 1 1. Now the second task that we know from our diagram, so let's scroll up to this diagram and see. So the first thing that we have to do is we have to, if you can see here, we are going to do the summation operation, and that can be simply done by np dot method. So you can see here we are doing a summation equal to np dot, which is basically nothing but my row vector x multiplied with the column vector weight. So I can just use np dot and plus the bias term, right? Very simple and straightforward. So this will take all my input rows, it will add the bias term to all the rows, right? Basically to the product of x1 dot beta 1 plus x2 dot beta 2 plus the bias term, as we saw in the diagram above. And then once we do that, it is very obvious that the first record where we had 0 values for the column x1 and x2, it will be just the bias term. So you can see 2.43077 and round it up to 9. And similarly, you can just simply do a simple mathematics and you will get this result for the 4 records. And once we have the 4 output from the summation, we are going to pass these 4 values to the sigmoid function, and sigmoid function will take this value and crunch this value within 0 and 1. So you can see all my values after the sigmoid function is between 0 and 1. So it's although the expected output are not even close to what we are expecting, but for the time being, let's assume that sigmoid function did what we asked it to do. Okay, so now we can see that sigmoid has given us the output as 0.9191 for the first record. So for 0 0 input, of course our expected was 0, but we got something as 0.919, which is wrong. Of course, I understand that. The second one should have been 0, the third one should have been 0, and the fourth one should have been 1. So technically all my 4 outputs are basically wrong. Okay, and the reason for that is, we started with a random value, and we should expect the output to be also random. Now in our next lecture, what we are going to do is how can we tell our network to correct this or keep updating this number so that we can reach to our expected values, and that is where we are going to use the concept of backward propagation. But the first thing that we wanted to explain is how do I take an input, feed it to my summation operator. Once the summation operator gives me some value, how do I feed it into my activation function, because this we are going to do n number of times. So that's why we wanted to dedicate one lecture only for this particular activity. And because we are going from left to right, we call this network, as I will just repeat it again, it's called as feed forward, because we are going from left to right. The data doesn't come back, it keeps going forward from the input to the summation, from the summation to the activation function, and then to the output. Okay, so I hope this gives you a clear picture of what happens in a feed forward network. In our next part 3, we are going to do the same activity, but then we are going to use the concept of partial derivative and see how we can move from the output towards the input so that we can update these weights so that eventually we get to our correct expected result. Okay, so I hope you have learned something new today. So please share your feedback and how do you like our videos, and because this keeps motivating us to produce more and more interesting content for you. Thanks and have a great day, and please subscribe to our channel Mirror Neuron, which means watch and learn.